We're now going to look at part B. Part B says, how many months will it take for the population of rabbits to increase by 90%? So again, we're starting with our equation, which models the growth of the population of rabbits that we got in part A. So we want to work out how many months, in other words, what is the time t in months that it will take for the population of rabbits to increase by 90%. Well, the thing we need to do first is work out how many rabbits there are going to be when the population of rabbits increases by 90%. So that's a starting point. We need the number of rabbits after the 90% increase. So in other words, we're going to increase the initial number of rabbits by 90%. So it's sort of similar to before. What we could do is we could put start. So this is at the beginning of month 1. And then finish is obviously at the end of a particular month, which we don't know. And the population increases by 90%. So at the beginning we know that we have 20 rabbits and that's worth 100%. What you have originally is always 100%. You increase 100% by 90%, you're now going to have 190%. So increasing by 90% is the same as multiplying by 1.9. Think about it. To get from the start to the finish, you can increase by 90%, or alternatively, you can multiply by 1.9. So to get how many rabbits we are left with, we multiply 20 by 1.9. So if we do that, that's going to give us 38 rabbits, and that's the key bit we need. We need to work out how many rabbits there are after they've increased by 90%. Okay, so we now know that n is 38. So we're now going to sub in 38 and then we're going to work out what t is. So sub in n equals 38. So we're going to get 38 is equal to 20 upon 1.3 to the power of t. So we're going to get the indice by itself. We're going to divide both sides by 20 to get rid of the coefficient. So divide 38 by 20 and that's going to give us 1.9. And that's going to be equal to 1.3 to the power of t. Now we've got the indice by itself, there's no coefficient. So how do we solve an index equation? Well, we're going to take the natural log of both sides. So natural log of 1.9, and that's equal to the natural log of 1.3 to the power of t. I'm now going to make this power the coefficient of the log using log rule 3. So we're going to get natural log of 1.9, and that's equal to t multiplied by the natural log of 1.3. Final act, we're going to get t by itself. We're going to divide both sides by its coefficient, the natural log of 1.3. So we're going to end up with natural log of 1.9 divided by natural log of 1.3, and that's just equal to t. So that's going to be the time in months when the population of rabbits has increased by 90%. We can now go to the calculator and type it in carefully. So type in carefully, and then that's going to give us 2.4464. So t is equal to 2.4464, and then we'll give our answer to 3SF, so our answer is going to be 2.45 months, and that is to 3SF. So you can actually appreciate from that how quickly this population of rabbits is increasing. Like, it's only it's not even 2.5 months later, the population of rabbits has almost doubled. It's increased by 90%. So you can see how effective this is, this model. The population of rabbits is increasing at a dramatic rate. Okay, and then that leads us nicely into part C. So if we go back to part C. Part C says, will the model hold for large values of t, and explain your answer. So remember, the model is based on this index equation that we've used to model the situation. Now, will this model or this equation hold for large values of t in reality? That's what we're talking about. This is the theory here, this is the model, but will that model what's happening in reality? Like, in reality, will the population of rabbits continue to grow forever? Well, the answer to that is probably not, because of several external factors. For example, there could be disease in the population which is going to eradicate or kill a lot of rabbits, so that's going to stop it from continually increasing. Or extermination, you could have a farmer going out and just killing them all, and then therefore the population is not going to increase. So therefore the model won't hold, part C. The model will not necessarily hold for large values of t, because in reality the population of rabbits could decline due to disease or extermination. So don't lose sight of these equations that we're setting up. These equations only model what's happening in reality. They don't, the problem with them is they don't take into account external factors. You know, this model here is just assuming population of rabbits is just going to keep growing and growing exponentially forever. But in reality, that may not happen. You know, rabbits could be, as I say, could catch disease and that could wipe a lot of them out. Or even just extermination. So that's the limitations of these index equations that we use to model different situations.